So far, we've been simplifying the heck out of these rational functions for what we've worked with in class, but now we're going to look at the graphs of these bad boys. So a rational function is one that can be written as a quotient. So if you got a function over another function, we get a function, and it's rational, so it makes a fraction. All right, and both of these are going to be polynomial expressions. Okay, so let's kind of look into our new parent graph that we have. So our new parent graph is y equals 1 over x. And if I were to graph this guy, the one thing we have to be concerned with are any excluded values. These guys are going to be important. And if we remember, our excluded values in a rational expression are what make our denominator equal 0. So in this case, what values of x would make our denominator equal 0? Well, x 0 would be 0, right? So x cannot equal 0 for this graph. It would not work. So if I were to state the domain of this graph, what x values would work? Well, basically everything besides 0 for x. So a couple ways I could state this. One thing I could do is I could say x has to be less than or equal to 0, or x has to be greater than or equal to 0. That'd be one way to state it. So basically everything besides 0. Or I could say all real numbers. I like to do this R with a line that represents every single number, but x cannot equal 0. Yeah, that's another way to put it. However you'd like to state it, but x can't be 0. What about for my y's? For the range, you might think that everything would work. But if I were to graph this, let's kind of take a look here once. I got 1 over x, and I'm going to zoom standard right away, so 6. So I can kind of see it. Looks like it's got a little hyperbola action diagonally. I'm going to zoom in a little bit. So I'm going to go 1 down to 2, zoom in. I'm going to put it right at the center, and I'm going to zoom in just a little bit here so I can see this a little bit better. So if you notice, x cannot be 0, right? So x can't be 0. There's nothing touching here. And actually, y also cannot be 0. It's not going to touch this x-axis as well. So y can't be 0 either here. So that's where it's kind of tricky. And why can that be? Well, what could I plug in for x to make y 0? Well, nothing, because if I try to plug in 0, it's undefined. It doesn't work. So y can't be 0 either, right? I can get really close to 0, but not quite 0. So I'm going to do the same thing here. I'm going to say all real numbers, but y cannot be 0 either. Would this be a function? What determines a function? Yeah, each input can only have one output. And if I did the vertical line test with this, drew a vertical line all over, it only passed the graph one time. So yes, this would be a function as well, right? Each input of x would only have one output of y. And what we need to notice is that these hyperbolas are going to have asymptotes, except instead of having diagonal asymptotes like we had in the past, they're going to be horizontal and vertical ones. So it's really a hyperbola that's rotated 45 degrees in this case. So we're always going to have a horizontal asymptote, which in this case, since y cannot be 0, my horizontal asymptote is y equals 0. It's that dashed line right here that kind of separates the hyperbola horizontally. Then I'll also have a vertical asymptote, and this one's going to be x equals 0. So I'm almost stating like which value of x and y cannot work to state the asymptote. And that's the equation of this line right here, this red vertical line right there. Okay, and if I notice in my parent graph, from the center of where those asymptotes meet, if I go over 1, up 1, that is the point where it starts changing direction, right? So if I go over 1, down 1, that's the point, or down 1, over 1, that's the first point. So over 1, up 1, or over 1, down 1, that's the first point. And that's where I'm going to consider my stretches when I start looking at stretches of this guy. So what will each of these graphs look like? Well, I can make a pretty good assumption. If I throw something at the end of it, usually that considers the y-intercept. So what do you guess is going to happen here? Yeah, this guy's going to move down 2, right? And if I take a look at that graph, what do you notice? It moved down 2. So I still have a vertical asymptote at x equals 0. But what happened to my horizontal asymptote? Well, yeah, it shifted down 2, so now my horizontal asymptote is at y equals -2. Well, if I looked at the next guy, I bet you could take a good guess. What happens when we put something with the x? Yeah, it moves it that direction, just the opposite way. So it's really going to move this guy right 2. So if I took a guess, what do you think my vertical asymptote would be? Yeah, it's going to change it to x equals 2 now. What about that's my vertical, right? What about my horizontal? Well, that's going to stay the same. It should still be y equals 0, right? Because it didn't move up or down. And if I took a look, there we go. So I got my horizontal at y equals 0, and then my vertical at x equals 2. What if I threw some stretches in here? Okay, the thing with stretches, the best way to think of it is almost like factor out the stretch. So in this case, what I could really rewrite this as y equals 2 times 1 over x. So this would have a stretch of 2. Whereas this one over here, I could rewrite this as y equals, I could factor out this 1/2 and put it as 1/2 times 1 over x. Right? So if I look, this first guy has a stretch of 2, and the second guy has a stretch of 1/2. Well, how's that going to affect it? Well, instead of going over 1, up 1, we're going to end up going over 2 before we go up 1, or over 2 before we go down 1. And same thing here. Instead of going over 1, up 1, we're going to go over 1/2 before we go up 1. And same thing. I'm going to go like up 1/2 before I go over 1. So, I go over 1/2 and I go up 1 right there. And I go up 1/2 and I go over 1, so right there. So it makes little points. So it almost like cuts it in half. Whereas up here I had a stretch of 2. So that means I go over 2 and then up 1. So there's my new point there. I go up 2 and right 1 down there. And the same thing over here. It just gets stretched. So over 2, off 1. So before it used to be, over 1, up 1. These are my old points on the parent graph. And it got stretched out. So these are the same. Vertical and horizontal stretches are the same. Act the same. That's kind of the interesting part of this one. So if I say a vertical stretch of 2, that'd be this. If I said a horizontal stretch of 2, that'd be that as well. And it would go up top just like that. So let's try to graph one quickly on our own. So the best idea is to draw in the asymptotes. So what can x not be here? Well, x cannot be 0 and y cannot be 0 for this guy, right? So I didn't get shifted up or down or left or right, so I should have asymptotes at y equals 0 and x equals 0. What do you think this negative is going to do here? Yeah, instead of looking like this, it's going to be reflected over the y-axis. Okay, so it should be in the other quadrants. And it's got a stretch of 3, so instead of going over 1, up 1, so if I look in here, instead of going over 1, up 1, it's going to be stretched. It's going to go over 3, up 1, and up 3, left 1. So it's going to be up there. And same thing over here. Over 3, down 1, and down 3, over 1, just like that. So it should look something like this. Just like that. Okay, let's do the same thing here. Let's draw in our asymptotes. Where is there going to be an asymptote? So it got shifted up 2. So I should have an asymptote at y equals 2. And then I should also have a vertical asymptote at, this is going to shift right 3. So I should have one at x equals 3. Okay, and then is there any stretch in this case? No stretch, because it's just got the 1 up top. So that means it's going to go over 1, up 1 from the center. And over 1, down 1 from the center. And then it starts to go along the asymptotes. Just like that. Okay, not the greatest drawing in the world, but pretty solid. All right, so basically we got the understanding of where the asymptotes lie. There's always a horizontal and a vertical asymptote. That the graphs get really close, but they can't be them because of our excluded values, right? Because like in this case up here, x could not be 3. So that means there's an asymptote at x equals 3. And technically y could not be 2 in this case because this guy got moved up 2. There's no way I could get a value of 2 here because I'd have to make this be 0 to get 0 plus 2, which I can't make that whole thing 0. So hopefully we're starting to get that idea of how rational expressions work. But yeah, asymptotes are the key. Stretches might take a little bit of time to get used to how that works, but hopefully we should be able to write an equation and graph a general rational expression like this.